Well, hello and welcome back. We're going to continue our discussion of analysis of variance designs. Now, in the previous videos, we've looked at two types of analysis of variance designs. One type was called a completely randomized design. And in this design, we had one factor which had different levels, and we measured our response variables. We had fertilizer that maybe had different percentages of nitrogen, and we looked at the yields. And the next type of design, we talked about a randomized complete block design, and this was rather similar to a completely randomized design in that we had one factor that we were interested in, but in an RCBD, we also included a block to remove variation caused by different groups. So for instance, we may have had different levels of fertilizer and nitrogen in that fertilizer. However, these were planted in fields that were in different areas, and we knew that these different areas had different moisture percentages. But we couldn't control for those moisture percentages. And so we used those areas as a block to remove this variability. However, suppose now that we're interested in moisture levels and nitrogen levels, and we want to see how these impact crop yield. So perhaps we would like to maximize crop yield, and we want to use moisture levels that we are controlling at a low level, which is perhaps 10%, and a high level, which is at perhaps 20%. But we also have these nitrogen percentage levels in our fertilizer. And so we've got a control of 0%, and then we're going to apply 5%, 10%, and 15% nitrogen respectively. Also, suppose we have 3 replications for each treatment combination. And we're going to call this a factorial design. Now, I've already read the data in for this design, and you can see that here we have our yields, here we have our moistures, here we have our fertilizers. Notice there are 3 replications in each combination. So we have a moisture level of low and a fertilizer of none. We have a moisture level of high and a fertilizer of none. We have a moisture level of low and a fertilizer of 5, etc., etc. And there are 3 replications in each of these combinations. This is the factorial design. We look at each treatment combination. Now, again, our moisture has 2 levels, low and high. Our fertilizer has 4 levels, and that is control 5%, 10%, 15%. R is going to be our number of replications per treatment combination. N is our total number of observations in the data set. And we're going to call Yijk, that's just going to represent the individual observations. So I'm going to say, well, A is going to be 2. These are our moisture levels, so it's either low and high, so I'm just going to call A 2. B, we've got 4 levels, and so B is going to be set at 4. R, our number of replications, these are 3. Capital N will be our total number of observations in our yield, and so that's 24. And then again, Yijk, that's just going to equal our fertilizer yield. So I've called this FertX, and so here I'm defining A2, B4, R3, and then N is 24, and now I've got my individual observations. And so you can see that if I just highlight Yijk, I get all of my observations. The first thing I'd like to do is create box plots because I'd like to see, is there a difference in any of these yields based on any of these? So the first thing I'll do is create a box plot of my moisture levels and see how moisture levels and yield are impacted. And notice, high seems to have a slightly lower median than low, but all in all, these look relatively the same. So now let's take a look at our nitrogen levels and see how yield is impacted by nitrogen levels. And notice, 15% appears to have the highest yield, while 5% appears to have the lowest yield. Well, that's nice. But remember, we want to determine if there's a combination of these moisture level and fertilizer levels that's going to give us the highest yield. So now let's take a look at a box plot of our yield based on these combinations. low and 15. So 10% moisture and 15% nitrogen appears to give us our highest yield, while high, our 20% moisture and 15% nitrogen gives us the second highest yield. But notice, 20% moisture and 5% nitrogen and 10% moisture and 5% nitrogen appear to give us our lowest yield. And so the question is, are there any differences in these interactions? Because that's what we would like to test. We would like to test and see if there's an interaction. And so our null hypothesis is going to be that our ijth interaction is 0. Our alternative is going to be that our ijth interaction is not 0. And we'll set this alpha at 0.02. The first thing we need to do, we need to find the grand mean of our data. In other words, we need to find the overall mean for the yield. And I'm going to call that y bar dot dot dot. And y bar dot 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 we can see is 79.04167. Next, we need to find our individual cell means. What this means is we're going to take the observations, let's say for this first one, this is the cell mean for low moisture using control. And so I'm just going to take the low moisture and the control. So I'm going to take these three values, add them up and divide by the number of replications. That's 3. And I'm going to do this for each of these different cell means. And so I'll highlight all of these and just run them. So notice y bar 11 dot, we get a value of 64.66667. And y bar 23 dot, we get 69.66667. After this, I need to find my marginal means. Now, I've got two sets of marginal means because I'm going to have marginal means for my fertilizer and I'm going to have marginal means for my moisture percentage. Marginal means for the fertilizer is going to be the sum of the yi dot j dot divided by levels of A. In other words, I'm going to take my cell mean for low and control and add to it the cell mean for high and control. Divide by 2. Cell mean for low and 5% plus cell mean for high and 5% and divide by 2. Cell mean for low and 10% plus cell mean for high and 10% divided by 2, etc. I'll run these. And then we're going to look at marginal means for moisture percentage, and this is the sum of the cell counts divided by the levels in B. And so here I have the marginal means for low moisture. And this is going to be the sum of my cell means in low. I'm going to condition on low, and I'm going to add up across my fertilizer cell means. And so I get, here I have low in control, I have low in 5, I have low in 10, and I have low in 15. And I divide this by 4. And likewise, I'm going to do the same thing for my marginal mean for my high moisture. And so here we have our marginal means for moisture percentage. Now I've created a table to show you what this is going to look like. And so I'm just going to run through this. And notice here I have the cell mean for low in control, the cell mean for high in control. The cell mean for low in 5%, the cell mean for high in 5%. The cell mean for low in 10%, the cell mean for high in 10%. And then the cell mean for low in 15% and the cell mean for high in 15%. But I also have these marginal cell means. So here I have the marginal for low. So what I've done is I've added up cell mean here plus cell mean here plus cell mean here plus cell mean here divided by 4. Here I've got the marginal for my high moisture level. And then across the bottom, I've got the marginal means for control, 5%, 10%, and 15%. And here I've got my grand mean. So we need to find sum of squares total. This is the sum of squares of our observations minus the grand mean squared. And so what I'm going to do is I'm going to look at these deviations between my individual observations and the grand mean. I'm going to square those deviations and I'm going to add them up. And so for my sum of squares total, I get 18,990.96. Now I need to find my sum of squares for treatment. Here I'm dealing with sum of squares treatment A. In other words, sum of squares of my moisture levels. And so I've got the number of replications times the levels in factor B times the sum of marginal means minus my grand mean squared. And so here, notice I've got, for sum of squares treatment A, there are 3 replications. There are 4 levels of B. So I'm going to take my marginal mean for low minus the grand mean squared plus the marginal mean for high minus the grand mean squared. And when I run this, we'll see that sum of squares treatment A, 1276.042. For sum of squares treatment B, this is number of replications times the levels in A times the sum of the square deviations of the marginal difference in B minus the grand mean. For sum of squares treatment B, that is number of replications times the levels in A times the sum of the square deviations of the marginal means in factor B minus the grand means. So what we get are 3 replications times 2 levels in A, and notice here I've got my control marginal mean minus the grand mean squared, plus 5% marginal mean minus the grand mean squared, plus 10% marginal mean minus the grand mean squared, plus 15% marginal mean minus the grand mean squared. And so we can run through this, and what we get is 16,344.12. Now I need the sum of squares for the interaction. And so for my sum of squares interaction, this is going to be the number of replications times. Well, now I have to look at my individual cell means minus its marginal mean for factor A minus its marginal mean for factor B plus the grand mean squared, or plus the grand mean. I'll square that, and I'm going to do this for each cell mean. I'm going to run this, and I'm going to get sum of squares interaction, which is 650.7917. Now I need to find sum of squares error. That is just sum of squares total minus sum of squares A minus sum of squares B minus sum of squares interaction. And so our sum of squares error we're going to find is 720. To find the degrees of freedom in a factorial design is very similar to finding the degrees of freedom in all other designs. Degrees of freedom of A is A minus 1. Degrees of freedom of B is levels of B minus 1. Degrees of freedom interaction are A minus 1 times B minus 1. Degrees of freedom error are A times B times R minus 1. And degrees of freedom total are A times B times R minus 1. To find our mean square error, this is very similar to other designs. Sum of squares A over degrees of freedom A gives us mean square A. Likewise, mean square B is sum of squares B over its degrees of freedom. Mean square interaction is sum of squares interaction over its degrees of freedom. Mean square error is sum of squares error over its degrees of freedom. And now we can find our F values. Much like the other designs we've looked at, the F value for A is simply mean square A over mean square error. The F value for B is mean square B over mean square error. And the F value for the interaction is mean square AB over the mean square error. Now we can find our probability. So let's take a look. Our F value for A, 28.356. Our F value for B, 121.0676. And our F value for our interaction, 4.820679. Now, I'm going to find the probabilities for A, B, and the interaction just using the probability of F function, where here I've plugged in F value A, degrees of freedom error, and I'm looking in the upper tail. Likewise for B and for the interaction. And so I'm going to run through and just run these. Now remember, we're testing for interaction, and so I want to look and see if there's a significant interaction. And what I see is I've got a p-value of 0.0141, which is less than 0.02. Therefore, there is an interaction. And as such, because we know there's an interaction, we do not go back and test the main effects. We do not go back and test A. We do not go back and test B. We've got an interaction. We know something's happening here. We can say that we're going to reject the null hypothesis and conclude that the interaction does not equal 0. And we've got sufficient information to say that there is one of these interactions, at least one, that is different from all the others. Well, this does this the long way. However, what if we decide we want to just use the ANOVA function? We can use the ANOVA function. We've worked with the ANOVA function. And notice I've got ANOVA, my linear model yield by moisture times fertilizer. This gives me my interaction. I've plugged in my data, and we can see that we get the same values that we got when we did this the long way. Notice 1 degree of freedom, 3 degrees of freedom, 3 degrees of freedom, 16 degrees of freedom. Notice our sum of squares were the same, our mean squares were the same. Here's our p-value for our interaction. We've determined an interaction exists, and so let's do an interaction plot and see what's happening. So here I want to look across fertilizer percentages and see how moisture yield impacts yield, or moisture percentage impacts yield. So when I do this, notice at 15%, low and high, regardless, give me the highest yield. It doesn't look like there's an interaction going between low and high at 15 going to 5. However, when I move from 5 to control, these interact. And then when I go from none to 10, they interact. When I look at moisture percentage, how do these fertilizer variations impact? And so now we can see, here I'm looking at moisture percentages, and I want to see what happens with fertilizer across moisture. Notice 15% is still the highest, but there's an interaction between 10 and none and between 5 and none. So now we need to determine exactly which one of these differs. So in order to do this, we're just going to run a Tukey analysis. And notice it gives us a whole lot of stuff. What we're interested in is which one of these p-values are significant. Well, there's a lot of them. So in a case like this, it's probably easier to list the ones that are not significant. Here I'm 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 not significant. And here I'm not significant. There are 26 of these comparisons because Tukey is comparing all of these comparisons. Notice our differences here. And notice that the largest difference is between low and 15 and high and 5. Also notice you've got your lower and upper simultaneous confidence intervals. So what might this look like? Well, we can create a Tukey plot, but it's going to be very confusing because given how large y-axis labels, it's very hard to tell which one of these are which. But we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 of our simultaneous confidence intervals that contain 0 and the remainder don't. And if we notice right here, this looks like our largest difference. And so what we could say is that it does appear that our values of low 15 and high 5 do have the largest significant difference. Okay, that's it for this video. In the next video, we're going to start talking about analysis of covariance. See you then.